Okay, all right. We'll start the session. Let others join by that time.
Ma'am,
Yeah,
the quiz will only be online mode, right? No paper and pen.
no, nothing. Only online computer based. The questions mode will be MCQs, MSQs, and very short answers like in numbers.
Okay.
You can answer. Kind of fill in the blanks. It will come. No, there will not be any justification or anything. Sentence like kind of answers.
Okay.
Ma'am, and when are we receiving the mock test?
Mark quiz, we don't have the plan to give them any mark quiz. If you have any doubt, you can practice the graded assignments and practice assignment questions. That will help you. Otherwise, if you have any doubt, we can discuss that in live sessions. We don't have the practice of giving mock quiz.
Okay, okay, ma'am.
Okay. Right. So I hope the another instructor would have taken a few introduction about this week. So we can start solving problems based on the topics we studied here. Before that, I want to just warm a little bit. So in week 4, the entire week in 4 modules, we'll be studying time domain analysis, about second order, first order systems, time response specifications, and about the steady state error, where this steady state error and the time response specifications is little important compared to the first two, because these are all basics and this is kind of implementation. Out of when you learn the basics properly, this implementation would be easy for you to do that. Right. So far we have seen some of the tools. First, we studied about modeling in first 1 or 2 weeks, like how to represent a system, how to define a system. And in second weeks, we have seen few tools to do that. For example, Laplace transform, and we have some knowledge about Fourier transform also. And now in the third week, we have studied few things about the transfer functions, how to mathematically represent, or in the control system point of view, how to represent a system in terms of input-output relationship. And in the fourth week, we are going to study the time response analysis. So out of these 3 weeks, now we are taking our steps into the time domain analysis. So out of these 3 weeks, so we have studied some basics, how to represent a system in time domain and frequency domain, and the tools to convert one from one domain to another domain, time to frequency domain. Now we are going to concentrate in this side, how to represent a system in the time domain and what are all the observation we can make out of the time domain representation of any system. That's what we are going to focus. The later part of this entire lecture, kind of week 6 to week 12, it will be focusing on the frequency side. So in frequency domain, how we can study something about the system or the nature of the system, kind of. So this fourth week and most probably the fifth week also will be focusing on the time domain side. Uh, Whenever we are representing a system with respect to t, we are going to see how well we will be able to study something out of the system. Right. For that, we have few basics to cover. For any system, if you want to represent in time domain, it tells how the system outputs evolves with time when an input signal is applied. So we can think this as a car that speed changes over time when pushing the accelerator. In contrast, if we think about the frequency domain systems, or frequency domain representation, it tells how the system reacts to different kind of frequency ranges. So if focusing on time domain analysis, the system's response, for example, I have a system and I'm giving one input to it and expecting some output out of it. So this output can be of two types. One is natural response, another one is forced response. So this natural response is like studying the system behavior due to its internal energy, or if it has some ability to store some energy. If we keep the system ideal, or if you don't disturb the system, if you are not giving anything as an input or a disturbances externally, how the system behaves for with respect to only its internal energy, that response, output response, are going to be natural response. On the other hand, if we give input and study how the system behaves, that is called as forced response of the system. So this is what we are going to study in terms of two important things. One is transient response, another one is steady state response. So this is the most important topic in this time domain analysis. So we are going to split the output response into two different category. One is transient, another one is steady state response. Right. Now, if I take some oral system, kind of this system. So, if I want to study the both the natural and forced response, this means, for example, if it is a oral system, it has one R, one L, and a voltage source. Let's take if it is there. And at first, I'm considering V equal to 0. So, how will I write IR plus L di by dt equal to 0? So, this will be, if I take I as common, this will be R plus L S, right? In terms of Laplace terms, domain. So this will give me, if I convert this to a time domain analysis, I will, if I want to represent in terms of time domain, I will get this, right? IL, that I consider some initial conditions also. And if I want to represent in terms of transfer function, it will be 0. Otherwise, there we are assuming some initial condition is there. And we are left with this exponentially decaying function. So this means the current decays exponentially when nothing is there. It is the behavior of the system when the voltage is equal to 0. So we call this as natural response. So we from here we know the current will decay exponentially when there is no external supply or any voltage given to the system. So this is what natural response tells. The next thing is forced response. We are assuming some voltage, V is equal to Vi of t. Some voltage we are giving. So there it was decreasing, exponentially decreasing. When we are considering some voltage, there will be one term here. Based on this term, there will be an exponential rise in the output of the system or current. That's what we are considering output here. So based on this both will change. We will see some problems out of this. How to find a natural response, how to find the forced response of any system kind of. Okay. Mm, I have a RL circuit, same RL circuit I'm considering. We want to study the natural and forced response, or we want to find the natural and forced response of a RL system. So I'm taking R is equal to 10 ohm arbitrarily, L is equal to 2 Henry, and I'm assuming initially the current was 5 ampere, not 0 for now. Okay. So we know the governing equations, L di by dt plus IR equal to 0 for finding the natural response. So when I substitute the value, IR is equal to 10, 10I plus, this is L. Okay. L is 2 di by dt equal to 0. This will give me di by dt plus phi I equal to 0. So solving this, I will get di by dt equal to minus phi I, and if when I solve, I will get I of t equal to phi e power minus phi t in terms of time domain. So here the time constants will be represented, this is in the, we know this is e power r by L, right? So we know here e power r by L is equal to 5. R by L is equal to minus 5 or minus. So R by L is equal to 5 here. So tau is equal to 1 by R by L, whatever time constants we have. So this tau can be called as time constant. This is another important parameter in a first order system that tells time taken for the system to reach 63.2 percentage of its final value. Since you would have gone through this before, can anybody tell why particularly we are considering this value 63.2? Or we can also say this is the time taken to decay 36.8% to reach 63 or to decay 36.8% of the overall energy of the system. Why particularly this value?
One time constant period. So that will be e power minus 1.
Yeah, you're obviously right. So for a system, first order system, your output response would look like this, right? E power minus t by tau. Where if whenever your t approaches your tau, your time constant, this becomes e power minus 1. So calculating this value, you will approximately get this. That's why we are considering this. So this time constants will tell how efficiently or how fast your system is going to decay or it's going to rise its response. So this is a crucial parameter in evaluating a first order systems or something. So from here, if you want to find tau, this tau will be 1 by 5, it will be 0.2 seconds. So the system would take for this particular R equal to 10 and the L equal to 2 for this kind of system, the system will take 0.2 seconds to reach 63.2 percentage of the final value. That's what we can conclude from this. Right. Next thing is first order systems that we saw now. The same thing. This is what this example also tells. You can work out on this to interpret how fast the system is going to respond. This is the explanation. Okay, response of first order system. We'll see one problem in response of first order system. So I'm taking first, I want to consider simple one, step response of a first order system. And I hope we are clear in orders, right? First order, second order. So first order means we have one energy storing element in the system, overall system, or you will see the highest order of the denominator would be 1. That's why it is first order. We call it as first order system. In RL circuit, L is the energy storage element, only one energy storage element. So it comes under the first order system. Right. Now I'm considering first order system like G of S is equal to 1 by 0.5 S plus 1, and I want to give a step input of 10 value. not 1. It's not a unit step input. I want to give a 10 step input, but find the output response, y of t. So this is a step signal. So I'm calling this just step response of a first order system. I'm giving input as a step signal. We know y of t by r of t is equal to, otherwise I will write in terms of this. Y of s by r of s is equal to a closed loop system. Here I'm considering g of s by 1 plus g of s h of s. If it not, it is a, assuming it is a negative unit feedback system. Okay. But we don't need to go until this point. First, I want to know, take this as an entire system. So I can write in terms of y of s is equal to g of s into r of s, right? For now, considering this as a closed loop system transfer function. So I'm going to write y of s is equal to whatever g of s it is given, 0.5 s plus 1 into r of s 10 unit step signal. So I'm considering this. I'm going to do a partial fraction to this. So 10 by 0.5 into s plus 1 by 0.5, it will be 20. So this will give me, this will again be 20. Considering 20 is common, will be 1 minus e power minus 2t, right? So,
It's s plus 2, no?
oh, yeah, b2, right. b e power minus 2t, right? Okay. So this is my output response. Y of t is the output response for a step response of a first order system. Similarly, you can work with the um, ramp response or parabolic response, where this will become 10t, 10t square kind of. So here also it will come. You have to convert this into a Laplace domain. That t will be converted, should be converted to a Laplace domain, and you will have some other value here, and there will be some other term here when it goes to other responses, ramp response or parabolic responses of the system. So we can see one example on that also. If I consider a ramp response of a first order system, I'm taking g of s is equal to 1 by s plus 1, the whole system. With unit ramp input, I want to give as 1 by s square. There is nothing, it's only unit, simple I'm taking. I want to find y of t, not y of s. I have given g of s, r of s. So we know y of s is equal to g of s into r of s. It will be 1 by s square into s plus 1, right? So taking partial fractions, a by s square plus a by b by s plus 1. This will give me, um, so there will be another term, c by s. So I will get, I'm just writing here, a will be a, b, c. So a will be 1. Oh, sorry, c will be 1 when you put this. And what else? S plus 1. B will also be 1. I guess A will be also 1. Right. So you will get a system, right? 1 by s square plus 1 by s plus 1 minus 1 by s. So this will give you t plus e power minus t minus 1. right? So this is your y of t. If you take inverse Laplace transform. So this is your ramp response for a first order system. Okay, right. So these are some standard test inputs. As we know, impulse, we saw this in week 3 or 2, I guess. Impulse step, ramp, parabola, parabolic signal. So this can be unity signal. Sometimes it can be non-unity signals. More than one, it can be like 10 in the previous examples. Okay. So I want to give you a handy note that you can refer to, but it's always good if you solve it by yourself. If I consider a system h of s that is of first order, tau s plus 1, then if I consider an input, output response, behavior of the system. So if I consider an impulse signal, delta of t, your output response with respect to this first order system would look like this 1 by tau e power minus t by tau. For example, if your system has 5, your tau is equal to 5, this will be 1 by 5 e power minus t by 5. That's how your output response is for the first order system with impulse response. Right? So this will create as it has e power minus t, it decays exponentially. For a step signal, step input, u of t, it will be like k into 1 minus e power minus t by tau. So here if you see, there is no dependence on the gain. Irrespective of the gain, whatever the system gain is, that is this k, if you choose impulse response, it will depend only on your time constant of your system. Based on your time constant, that's how fast or slow the system output response is going to decay. If you consider a step response, then it depends on your gain of the system and also the time constant of the system. So this will give you a behavior that has a smooth rise to a steady state value. And that could be a zero steady state error or some other steady state error that we will see later. If I consider a ramp input R of t, then this your response output response will look like this. You don't need to by heart this. If you solve, you will get this. So this will grow linearly, exponentially. It will increase as it depends. There is a dependence on the tau here also. It will be added together. Your time constant. That's it. This is a small observation for a first order system. I think we have covered most of the first module, right? Yeah. Now we'll see what is there in second module. It is of second order systems. So this module will explain about second order systems. Okay. Similarly, what we saw for a first order systems, as it is second order, there it has two energy storage elements, and their natural response and forced response will change accordingly. So there will be another term added together. For a second order system, this is your governing equation that tells about the natural response of the system, because we are considering the any no energy, kind of no input. If the input is zero kind of situation we are considering. So your natural response will look like this. There will be some spike initially because of your um, this will be zero, right? So yeah, we can simulate this and see. Before that, we will see what is a second order system first. So second order system. Your first order system would look something like this: k by tau s plus 1. This is a general explanation for your first order system. If I want to see the second order system, then I can say it would look like this: omega n divided by s square plus 2 zeta omega n s plus omega n square. So this is how your this is how your second order system would look like. Where there are important terms. This zeta represents the damping ratio and the omega represents the natural frequency of the system at which this oscillation is happening. Right? So here we know that there will be two energy storage elements. For example, whatever we studied so far, that in the modeling we studied mass spring damper system. It's an example for a second order system. RLC circuit is another example for the second order system. So in this representation, this omega n represents how fast it the system would oscillate without damping. So if it has high frequency, the oscillation will also be very high. This damping ratio represents how quickly the oscillation dies out. Because there will always be a trade-off between two parameters, right? So this omega n tells how fast the oscillation would be uh, when there is no damping. For example, when zeta is considered to be zero. So zeta comes into the picture to make this oscillation dies out. So based on the value of zeta you are choosing with respect to omega n, because both are interdependent, with respect to omega n, whatever values you are choosing, you will be able to die out the oscillations very quickly, that quickly. So we have to play around this zeta value on omega n to get a desired output response. For example, if I have a system that gives an output like this, I don't want any unstable output, right? This is exponentially increasing. Oh, if I want to bring down that output to something like I want, it should rise for some time, and then it has to be at this point steady state error. There should not be any error between the set point and the output response. So based on my requirement, I can play around with choosing this zeta value and omega n so that I can bring out this system to this kind of output response nature, but it has some limitations. We cannot do this to all the systems. How well we will be able to do that, that's what we are going to study in this later lectures. Okay. Now, so the I just want to say the relationship between poles and the second order system is from this, it's available in the PPT. So from this, we can find the position of the poles as zeta omega n plus or minus j omega n root of 1 minus zeta square. I hope this is correct. So this gives the location of the poles with respect to the system based on your omega and zeta value. Okay. Right. And also, the second order system exhibits different kinds of responses, output responses that can be classified into four subcategories. One is underdamped. We have seen some sneak peek of this during the first week. We are going to see this in detail. Second is critically damped. Third, overdamped. Fourth is undamped. So, based on the zeta value, this can be classified accordingly. So, for an underdamped system, the zeta value would be considered between 0 less than or equal to zeta less than or equal to 1. For critically damped, it's very ideal case zeta equal to 1. So, this is an ideal case. No perfect system in the real time environment would do this, but we keep this for studying how, sorry, how it will be when it reaches 1, like zeta equal to 1. And the next one is zeta greater than 1 comes under overdamp. And when there is no zeta, there is no damping as we consider here in the first case. So that will comes under the undamped system. So in this case, the system will just oscillate around a point. So this zeta comes into the picture to make the oscillation dies out, right? So when there is no zeta, the system would ideally oscillate. So for the first this category, we know how the system response would be. So for the next three category, we will see if this is a output response I want to see. mm, T, considering T, Y of T. As time goes on, how the different responses would look like. Ideally, as I said, for a zeta equal to 1, it would look very ideal. Your critically damped system would look very ideal. There will not be any overshoot or any delay. It's a perfect system. When you have an underdamped system, your response would look something like this. Eh, response would look something like this. Okay. For a overdamp system, your response will have too much delay or it's very sluggish to reach. And we are not sure whether it will reach the steady state. That's I'm not sure. It varies with respect to the system. That comes the second part. Here we are only analyzing the transient part of the system. So how the transient would be when you switch on your system or if you energize your system, what is the actual immediate response of the system? That's what has been classified here into four different categories, right? And we know that if it is a undamped, it will be just oscillating around this point, kind of this. There will not be any. It won't die out at all. It will just oscillate around this point, right? So now there are many studies here. Ideally, I want a underdamped system. Most of the system, or I would say most of the systems we consider is would under comes under underdamped system, and we will be interested in how well we are going to reduce this overshoot. This we call it as overshoot because this is your steady state or set point value. Ideally, I would expect my system to track this point, but it increases to this point, right? This is the peak it got. So this is the overshoot I would expect. And it takes this much time to reach the steady state. For example, this much time to reach the steady state. Right. So ideally, I would play around how much overshoot I want and how quickly I should my system response should reach the steady state value. To get this desired output, I will play around with this zeta and omega. Changing this zeta and omega n will change the overshoot value, and settling time value. So we'll see each and every category now. What are all the technical terms to call it? Right. Before that, um, yeah, I think we have covered pretty much of everything here. Transient and steady state responses we have covered for a second order system. Damping ratio and natural frequency. And there is another term called damped frequency. This is a frequency tends to oscillate. Frequency represents the oscillatory behavior of the system in the presence of damping force. Here, the natural frequency is the absence of omega and absence of zeta. Here, even if there is a zeta, there is some zeta available, damping available, how the system oscillation would be. That's what the damped frequency refers to. It will be called as omega d. This is like we'll take partial fraction of this and we will use inverse Laplace transform to find the output response of a system for a second order system. And we discussed this poles location, right? Here, second order system and their poles are here. So based on this pole location, your stability will vary. Stability of a second order system will vary. And again, it depends on zeta and omega. Playing around with zeta and omega and also influence your stability of a system. You can, that's what I told. Sometimes we can convert this type of behavior to this type of behavior, whatever stable behavior, right? So based on this zeta, changing zeta and omega and we will be also be able to influence the stability. Okay, okay. We'll solve some problems on this. So this is, I'm just writing the actual representation of a second order system here. So can you compare these two and find the zeta and omega n value so that you should say what is the nature of the system, whether it is underdamped, undamped, or overdamped, or critically damped. Can you find it and tell me? Just find omega n square is equal to 25. Then what the n would be. Zeta 2 zeta omega n is equal to 4. If you find omega n, you can substitute here and find the zeta value. Find zeta value and put the zeta value along with this classification. If zeta comes under 0 to 1, how it is called. If it is equal to 1, how it is called. Kind of based on this zeta value, tell the classification of the system in the chat box. Right. 0.4 underdamped Manoj form. Rest of the people.
Ma'am, omega n is 5.
Okay.
Omega n is equals to 5, and
Okay.
our eta is 0.4. So
Okay.
100.
Yeah. Good. Okay. Everybody else,
Yeah, same, ma'am.
are you getting the same answer?
Oh, yes, ma'am.
Yes, ma'am.
Okay, right. So now it's okay, right? So your system would be under damp system because it comes under 0 less than 1. Just right. Our system would be under damp in this case. Okay. Now I will give. I want to find the step response of a second order system as we did for the first order. I'm considering zeta to be zero point 0.4, omega n equal to 5 as in the previous sum. So I want to find y of t. How can we find? So when you revisit your PPT or in the lecture video, you would see a step response for a second. This is the impulse response of a second order system. Similarly, you will find the step response of the second order system here. Right? Now take this, write it down in your notes. Consider this for a under damped case. This is so. As I consider the same z and omega n, we can say this is a under damped system as we found, right? So I'm going to use the same here. Right. Just consider this under damped case and use this output response. Use this output response. I'm going to write it here.
Ma'am, should
Yeah,
we memorize this for exam?
no need. So if you have this value, you can very well get this, but we don't test on your memory. You don't really need to memorize this, but you should know how this comes.
Okay.
That's it. So for understanding the problem and the nature of the things, I'm solving this problem. Otherwise, you should. We won't expect you to memorize all those things. If needed, we will give this in the exam itself.
Okay.
Formulas and
Okay.
right. So can you substitute zeta value and omega value in this and find the y of t here? I know it's little complicated, but it will help you understand few other formulas that is needed to solve this.
Yes, ma'am. Just give 2 minutes.
Yeah, yeah. Take your time. First, you need to know how to find the omega d. So I can help you with that. Omega d, it's also available in the presentation if you find. This is omega d value, and I think you need that's it. So, okay, you would have find some value here. Why we are doing this is, if you put this in MATLAB and if you try to simulate it, you can use LSIM or plot, whatever value you want, whatever way you are representing. You will see the nature of the system or the nature of the response here for the given value. Something like this, you will have some few overshoot and have some settling time to reach the set point. Okay. You will see it will be little oscillatory, but ultimately it will be stable. And you can play around this zeta and omega value. If you give this entire expression in MATLAB and change the zeta and omega value, it will generate automatically all the figures, all the plots, how for different zeta and omega n value the system would look like. Okay. So that's it. Similarly, you can use different responses, RAM, parabolic signal. We never really use parabolic signal anywhere, but it's one of the basic testing signals. You can use that and see. And this is another important topic. It's in time domain, time response specification. So whatever we saw bluntly so far now, we have some terms defined to it. For example, we if this is a set point and if it has, so here there is a defined expression that this we call it as overshoot, and the time taken to reach this value we call it as peak time, and the time taken to reach this point, like the steady state point, we call it as settling time. So like this we have definite formulas or definitions or something to hold on, where everybody can use interchangeably. That's what we are going to see right now. So this is a common explanation for it for any under dam system. So because we only expect this response in terms of under dam system, which is a very vast real time system responses. So here, if you see, maybe at this point it is settling. We have peak overshoot here, MP, and there is TD, TR, TP, TS. This many things are there. So MP, TD, TR, TP, TS. So we are going to see all these five definition one by one. The rise time, first one is rise time, we call it as TR. So the rise time is time taken to rise from 10% to 90% of the final value. Just not a very random, but we want to see this small portion we don't need, and also the highest portion we don't need. Just in between the overall maximum length we are going to study, just we pick out the 10 to 90%. It can also be 5 to 95%. That doesn't matter. But randomly from 10 to 90%, we are going to see how much time it takes to reach that point. Okay, right. And for that, the formula would be, so this is taken from the solution or the output response of a second order system for undamped case, where theta we have considered cos inverse of tau. If you put substitute that, you will have the rise time explanation. And if you want to see this derivation in detail, you can look for this in your reference books in Norman and Nice or in Ogata. They have explained how this particular formula would come from this output response of this under dam systems. So this is your ultimate formula that this you need to memorize. Actually, this comes under the remembrance category. So you have to memorize this formulas, all the five formulas to solve the problems during your exams. Okay. So your rise time would be pi minus cos inverse of zeta divided by omega into root of 1 minus zeta square. Otherwise, it can simply call like this. If we give theta in the question, you can use this formula. Otherwise, you can use this extended formula, which has only zeta and omega n. If you know only the zeta and omega n, you can use this. And this rise time varies for all zeta values. For example, if zeta is nearly zero, near to zero, then you have too much oscillations. See this blue diagram. I will just show this. So if your zeta is nearly zero, you will have too many oscillations. As we discussed, there will be oscillation and it won't die out, right? When zeta is nearby zero. There we have too much oscillation and your peak time, your overshoot will also be high when compared to the zero value. So as zeta increases, your overshoot comes down. Means your oscillation is getting died out. Right? The next important specification is the delay time. Delay time is the time required for the response to reach 50% of the final value. So this is the output expression of the delay time where it depends only on zeta and omega n. So if you want to see, this is the zeta variation. For example, as zeta increases, as I said that time to come to the steady state value is also getting, delay time is here. This is also getting increased, right? Here. So it's the time to reach the 50% of the final value. So when zeta is nearly zero, it reaches little fast. But when zeta is nearly 0.7 or something, it reaches little late to reach the 50% here. 50% of the values. So this is the interpretation of the delay time with respect to the tau value. Just understand the relationship between these values. And the next one is peak time, where the formula or the representation of the peak time is this. It is also depending on omega and zeta square, where here if you see, your peak time is this. Whenever overshoot increases, peak time will also increase, right? Because too much of overshoot will give too much of peak time. So same, when with respect to the overshoot, this will also be increased as zeta decreases. And the formula for peak overshoot is this. It will always be represented in terms of percentages. So as tau increases, your overshoot will decrease, so your peak overshoot value will also decrease. Settling time is time taken to reach the steady state value. And settling time can be considered into 2% and 5% tolerance. For example, if this is your set point and it takes this much time to reach here. So 5% and 2% tolerance will be calculated at 2 points. Just different ways of calculating this. So whatever percentage of tolerance we have asked in the question, you are going to consider that. If you ask for 2%, you will consider this formula. If you ask 5%, you will consider this formula. That's it. It's based on your time constant of your system. And I guess I have covered everything. And this is another relation between omega n and peak time. We'll solve few problems in this that will give you a little more idea about this. And going to consider the same system. Zeta is equal to, a different system. Zeta equal to 0.5, omega n is equal to 4. So your system would look like 4 square divided by s square plus 2 into 0.5 2 zeta omega n, right? S plus 4 square. So this will be 16 divided by s square plus 8, 4. S plus 16, right? This is your system. For that, you are asked to find TP, peak time, settling time, peak overshoot, rise time. This is just a warm up for you to memorize your formulas. Just try writing the formulas by yourself and finding these values so that it will be on your mind. Write the peak time formula, substitute the zeta and omega n value here. Just you can just write zeta as 0.5 and omega n as 4. Substitute it there and find the answers. Put it in the chat box. MP in percentage I want. If it is difficult for you to look up for the formulas, I can also help you with that. Just substitute here. Settling time would be for 2% I'm considering. Since it is a percentage, I'm putting 100 before that. Otherwise, there will not be any 100. Zeta pi divided by root of 1 minus zeta square. Everything is in the bracket. And rise time would be pi minus cos inverse zeta divided by omega n into root of 1 minus omega n, zeta square. I am writing this because I didn't give any theta value, right? So I'm writing the straightforward formula. Just tell me the answer. Always write in terms of with units. Okay, don't forget to write units when you find these specifications. I'll give you 2 minutes. Anybody found? If you found the answer, please put it in the chat box.
Yes, ma'am.
Okay. Okay. Overall takeaway from this is whenever you increase your zeta, your overshoot will come down, and also your response will be slower. On the other hand, if you increase your omega n, that parameter, your response will be faster, and it depends on the system how the overshoot will be. So always you want to balance between the speed and the stability. If oscillation is too much and overshoot is too much, then your system will become unstable from the stable region, right? So always try to pick up the faster response with proper stability base. Okay, Gayatri got 0.61 seconds as rise time, 91.91 as peak time, 16% overshoot, and 2 seconds settling time. Okay. Again, I want to insist that whenever you are writing your answers, please write with units, because when you come to end semester exam or something, there might be some pen and based paper based exam. So there, if the peak overshoot has been asked in a percentage, if you write it in 0.6116 instead of 16 percentage, then your answer would be zero. We cannot give any marks for that, not even considering the step marks. So you should be careful in what units the question has been asked and you have to answer. according to that. Then only you will get full marks. Okay.
Okay.
Right. What else? Okay. Effect of extra pores that we have to see. Effects of zero you have to see. Okay. Right. Now we'll solve some problems on effect of zeros and effect of pores.
So MP, if it is not percentage, we can just write it as without units, no?
Without units, 0.16 is enough. If
Okay.
it is asked in percentage, it should be in percentage. You
Okay.
should multiply 100 with it.
Yes.
Okay. Now we'll see effect of zero. Effect of adding a zero to a system or for a second order system. This adding zero, for example, if this is my system, pole zero representation of a system, second order stable system will have poles at left of the explain. Since it is a second order system, there will be two poles and there might or might not be any zeros that we are not going to consider, that we didn't consider so far. Now we are going to see adding a zero somewhere. It can be here, 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 or here, or so far from your poles, or far in the right hand side. So adding zeros to your second order system, how it is going to affect your system. That's what this topic suggests. I'm considering a case where I'm adding a zero close to the origin, somewhere here. And I have another case where I'm adding a pole far left, somewhere 10 to 12 times from the origin. And another case, I'm going to add it near a already pole and right to the pole, on the pole. So we are going to see this in detail, how adding a zero will be a problem or it will be helpful. For example, I am taking two responses, G1 of S I'm taking. It's a general response to zeta omega n s plus omega n square m. And in it's not omega n square here, it's just omega 1, right, in above. So you have to compensate for that also. S square plus 2 zeta omega n s plus omega n square. So this is a two different system. One with zero, one without zero I'm taking. And I'm going to consider same omega n for both, omega n zeta for both. Same, omega n equal to 5, zeta equal to 0.4. Okay. Right. For the first system, G1, your omega n is equal to 5, zeta is equal to 0.4. So if you find the omega d with respect to zeta, or how the oscillations will be in the presence of zeta, 0.4 is omega n root of 1 minus zeta square, 5 root of 1 minus 0.4 square. 0.4 square is 0.16. 1 minus 0.16 will give me 0.484 or 0.84, right? Yeah, so it will give me 5 into around 0.9, it will 81 if I approximate. So this will give me around 4.5. Your omega d will be closer to 4.5 frequencies of oscillations. Okay. Now I'm going to find other few parameters to identify the nature of the system. Your peak time would be pi by omega d. Since you find pi omega d 4.5, this will give me 3.14. 4.5. This gives me around 0.6 seconds. Okay. Right. Overshoot if I find MP percentages e power minus pi zeta minus zeta square, where zeta is 0.4. If we put this in calculator, comes around 0.25. So it will be 25 percentage approximately, let's take. And the next thing for this, okay, set. Now, instead of finding like this, we can simulate it, I guess. So if we want to find this for this like this, we need to find the inverse Laplace transform, and we have to find all the with that O of t output response, we have to find the time domain specifications. Instead of doing all this by hand, it takes time. We can simulate and see. Okay, actually, ultimately, what I want to tell is adding a zero will increase the initial slope. So if we want to, if your actual system look like this, for example, it told peak time would be 0.6 seconds and your overshoot will be 25% from your set point, right? So it generally looks like this. Adding a zero would shift your initial slope little bit than the previous one, and the rise time will decrease and your overshoot will increase. It will decrease the rise time and it will increase your overshoot. That's what the adding the zero would do for your system. Wait, I will show you. Okay, so I'm taking P of S. First S is equal to PF of S. Okay, and in G1, I'm considering what was theta here? 1 divided by S square plus 2 zeta omega n. 2 10 4 10 4 S plus omega n square would be 25. This is G1. G2 will be x plus 2 divided by the whole system as it is. So your yes is there. Okay, this is your G1 and this is your G2. If I do a step response, step of G1, this is your step of G1. I will put two figures. Okay, so right, see, I will do one first. Okay. Right. This is your step response of the first system G1 and step response of the second system G2. If you see the step info, figure 2 is G2, okay? If you see step info, the rise time was zero point 0.2 for the first system, but it is 0.07 for the second system when adding the 0. As we said that it will bring down your rise time. So it brings down the rise time effectively from 0.2 to 0.07. And the settling time here was maximum is 0.05. Settling time maximum was 0.17. It pulls down or it slows the response, slows down the response. The adding 0 slower the response, and the overshoot was here is 25, where the overshoot here is 115. It's very much, right? More than 100% is increased. So if you see this, this was a set point here. 0.04 was a set point here. Since it is an open loop, it's just 0.04 is a set point, not 1. And here it is 0.08, but it increased till 0.17 or something. Yeah, 0.172 is the amplitude. So it has 115 percentage of overshoot. It's more than 115 percentage of overshoot. So it increases the overshoot but brings down the rise time. Similarly, if we see adding a further zero, for example, I'm taking the same and I'm going to put it over very far in the pole zero plot. It's very far to the left, right? So if I put that, we'll see how the system would look like. Figure step of G3, step info of G3. And I want to do sleep state, small, clear up. Right. So these are my transfer function. OG3 is not there. And if you see, this is the step response of the second system. If you compare the first system and the third system, it looks more or less similar, but we'll compare it with the actual value. Rise time is 0.27, this 0.29, and settling overshoot is 26, here it is 25. So from this, can we say keeping the zero very far to the left doesn't affect the system as much as it looks, right? So moving this zero towards the origin will influence the system very much, which decreases the rise time and increases the overshoot. But when we push the zero towards the left of the S-plane, this brings down, this doesn't affect the system much, the nature of the system much. What if we include a right hand side zero? S minus 2 is x minus 2. They the same. I'm just including a right and 0 for the fourth system, and we'll see. Three, 4. S minus 2. You see, it's a right and 0. Oh, it looks very bad. The step response looks very bad. See, it has started and has taken a dip. The negative 0 has introduced a dip or a delay in the system. When you compare your rise time, it's 0.14. It's again decrease the system's rise time because it is near the origin, and your overshoot is significantly increased. So whenever your response was very bad because it is a negative 0. Negative 0 will introduce a delay or a dip in your system, and that will make your system minimum phase system, where minimum phase is not as like we are not interested in minimum phase system. We will be sorry, it will make the system non-minimum phase. Okay, we will be interested in minimum phase where the zeros lies in the left of phase plane because it greatly affects the stability of the system. Right, and you see, it was never settled. So it's getting settled, but if you increase the time, you will see still it is getting oscillated. Okay. So yes, the takeaway here is whenever you are keeping your 0 near to your origin, it will affect the system where that affected part would be it pulls down the rise time and increase the overshoot. But if you keep your zeros farther, like to the left or right, it won't affect the system much. Similarly, there are studies that tells the position of zeros, adding an effect of zeros, and I have to change the system entirely. So it should be a first order and adding the zero. This becomes a third order system. Then. So we'll keep that with this one. Okay, I hope this is clear. We have one important topic left, that is steady state error. Okay. I hope I can explain it here. So E of S, how this E of S generally comes? If this is G of S and you are giving an R of S, and you're getting on y of s. So this is a open loop system. So when we consider a closed loop system, this becomes r of s, same g of s, y of s, but we will have one feedback as h of s here, and we'll give this back to the system. So here, if we consider this, if we rearrange this, g of s, y, and it will be h. So this is plus, this is negative, right? So this part becomes the E of s, where E of s is the difference between R of s minus this whole part, where it comes from here, from Y of s to this whole part. So you will write the whole feedback. What happened? 1 minute, my stylus is never. One minute. Your whole feedback part, right? So now the steady state error is that when you find if this is your set point, then if you have an underdamped system response, and if it gets settled here instead of here, for example, we are expected it to settle here, but instead of that, it settles there. So the difference between the actual value of your output response and the set point, so actual minus set point, this gives the steady state error. This is actually the steady state error. So far, whatever we have studied, TR, TP, percentage overshoot, and settling time, everything, this corresponds to transient response analysis. So when we started off this session, we have discussed there are two different responses, right? Natural and force. So out of this, we will also started to study in terms of, sorry, we classified this in terms of a transient and steady state. We wrote in that PPT. So far we have studied this transient response. Now, in terms of steady state error, we are going to study the steady state response of the system. So transient response occurs at that point of instance of the giving energy to the system or giving input to the system. When a system is ideal, we are just giving an input. The immediate response of the system is the transient response at that moment, at that spark, what it is happening, how fast it is going. For example, if you turn on a switch very quickly, a spark would come. That is a transient response. And after that, what was the current in that switch? That during that spark, the current can go up to 7 to 8 times of the actual rated current. So that is the transient response of that particular switch. So that is a peak overshoot of the output response, the current measured. And after that, after the spark goes out, there will be some nominal value of current. That is the steady state value of the switch. So if the switch is designed to operate at 4 ampere, but it gives out only 3 amperes or it gives out 5 amperes, the difference between the 4 and 5 is the steady state error. It should not be there. Then you cannot say the system is good. So it has some steady state error. You have to bring it down to 0. Ideally, a good system will produce steady state error 0. If there is no difference between the actual and the set point, then it is okay. For example, we will expect our AC to be, if we set at 24 degree, we will expect it to work at 24 degree, right? If it works in 23 or 25, then it has a steady state error. We don't want that kind of system. At least we don't appreciate those systems. Right. So I want to give small lookup table that you can refer to. When studying a steady state error, as we discussed, we have different types of responses, right? Impulse, step, or what else? Ramp and parabolic. So when studying this here, this this involves R of S also, right? E of S is equal to R of S into feedback. So this R of S can varies with respect to this input. So as we vary the input, impulse, step ramp to parabolic, how the steady state error will change. That's what we are going to study. So when you give a system, and it also depends on the type of your system. Type, if you want to recollect, type 0 system is there is no poles at the origin. No pole at origin. Type 1 means one pole at origin. For example, S is equal to 0. One S will be at 0. 2 means 2S will be at say 0. It works as an integrator. One pole or two poles is type 2. And if there is no pole, it is type 0 system. Based on this will change. Right. We'll see that here. Okay. So if you have a steady state error and how can I start this? First, I will say the relation between the input and the characteristics. For example, whenever you use a step input, we correlate that with the position. When we use RAM, we correlate that with velocity. When we use parabolic signal, we call that impulse will be constant. Okay. Parabolic, it will be correlated with the acceleration. Why it is being correlated is that during our first 2 weeks, we saw if we have an impulse response and if we add it together or if we integrate it, we will get a step. Similarly, if we integrate it again, we get RAM. If we integrate it again, we'll get parabolic. Similarly, if you integrate a position, natural or what you can say is real time parameter. If you integrate a position, you will get a velocity, and if you integrate a velocity, you will get a acceleration. Right, this will be taken out from any constant value that uh, 1 meter, 2 meter. If you add 1 meter 10 times, you will get 10 meter position, right? It's like work done from 0 point to the point you last end point. Right. So similarly, if you do the reverse, you have to do the differentiation to get back all those parameters. That's the relation between the input signals and the actual error constants we are going to find. So if someone asks what is a position error constant, then it is understood that step signal has been used for that system. If it is velocity error constant, then it comes from the ramp input. If it is acceleration error constant, it comes from the, it comes if the system if the input of the system was parabolic signal. Okay, this was clear, I guess. Now, this is what I want to explain another time. Sorry for all this mess. I didn't check this. It was from the previous run. Okay. So we have this R of t minus y of t. So he of is situated here. So it will be R of s minus the entire loop from here. right? That's what we have written, where y of t will be elaborated into r minus y, where y is the g into r by 1 plus g, because it is a negative feedback negative unity feedback system. So it will be g by 1 plus gh, where h is equal to 1. And if you want to write it in terms of y, r will be multiplied here. That's what it's been written here, and this r is here. So if I simplify this, if I take r as common, and I would be having 1 minus g by 1 plus g, it will be 1 plus g minus g by 1 plus g. This will get cancelled. 1 by 1 plus g will be left out, r into, where that's how we got this r by 1 plus gs. So if we want to find the steady state error, there comes the final value theorem for the rescue. So when do you use a final value theorem? If this is my set point, and if I want to know where my output response is going to settle, that's where the final value theorem comes. So if you implement final value theorem, or if you substitute final value theorem for this transfer function, you will get this limit s tends to 0, g of s into g of s. That's what final value theorem suggests for any transfer function. Since it is a transfer function of a error signal, it is e of s. So it will be, this g of s will be replaced by this r of s by 1 plus g of s, instead of g of s by 1 plus g of s into h of s. Right? This is your steady state error. Now, I am writing it here. E of ss is equal to limit s tends to 0, s into r of s divided by 1 plus g of s. If your r of s is step, so I'm starting from step because that impulse is just a constant. So your step signal is 1 by s. In Laplace transform, it will be 1 by s. So I'm going to write equation 1 as E of s is equal to limit s tends to 0, s into 1 by s divided by 1 plus g, right? So this and this s will get cancelled. Your E of s will be limit s tends to 0, 1 by 1 plus g. Keep this in mind. We are going to revisit this again, if it is a step. Okay, right. Now, similarly, I'm going to write for different values. When r of s is equal to 1 by s square, where this is step, this is ramp. When it is ramp, E of s equal to limit s tends to 0, s into 1 by s square divided by 1 plus g. This will give me limit s tends to 0, 1 by s will be there into 1 plus g, right? Similarly, you know, when r of s is equal to 1 by s cube, that is parabolic, this will simply be 1 s will be added in the denominator, s square into 1 plus g, right? Now we have three different expression for three different inputs. When it is s cube, it is s square here. When it is s square, it is s here. E of s is s here. Now I'm going to write this. Going to write this. This is input 1 by s, 1 by s square, 1 by s cube. This will become, the limit s tends to 0 is common. I'm not going to write again and again. It will be 1 by 1 plus s, it will be s into 1 plus g, 1 by s square into 1 plus g. Now, so we have found this from the base E of s value. If you have any doubt in this step, please ask me now itself. We are going to derive further. It won't be confusing for you. Any doubt so far?
No, ma'am.
Okay,
No, ma'am, no, it's clear.
okay, right. Okay. Now In the next step, substitute S is equal to 0 whenever possible in the previous steps. So if I substitute S is equal to 0, this will be same 1 plus G. Here, this term will go 0. Instead of that, one minute. Okay, I'm writing it here. For RAM, it will be limit S tends to 0, 1 by S into 1 plus G, right? So when you want to substitute this, you have a numerator. So we'll take S as common. If I take this, it will be 1 by S. I want to put 1 S here. So I will take 1 by S here. I can write it in terms of this, right? 1 by S into 1 by S. That will make it S. Into it will be S into 1 by S 1 plus G. So I'm getting confused here how this can be expanded. Yeah, right. Yeah, it's G of S equal to 1 by S into 1 plus G, right? If I multiply 1 by S into S here, then this will be 1 by S into 1 plus G. As S tends to infinity, as S tends, because it is limit S tends to 0, right? So as S tends to 0, this becomes infinity. Again, it's wrong.
The correct only, ma'am. It goes to infinity.
It's correct only.
Yes, sir. Yes, ma'am.
1 by S divided by,
Because the type 0 system, only the position is constant and the next two are infinity.
this S is common for both, right? This S is common for both. If I multiply it here, 1 by S into S, 1 plus G. So this will give me 1 by S by 1 plus G. If S tends to 0, the above term tends to infinity, right?
Yes, ma'am.
want to derive KV from this.
In the lecture, sir just puts S is the first S is equal to 0 and keeps the next S into GFS.
Okay, then it will be S tends to 0. If I put in the first R of S is equal to S square for RAM, it will be 1 by G as we derived earlier, right? So this will give me S tends to 0. 1 S will get cancelled. Then I will be with 1 into S plus 1 plus G.
Here
And
he
my
expands it into S plus.
multiplying
No
numerator.
multiplication, man.
Ah,
Denominator becomes S plus S into G.
S plus S into G. Okay. Oh, as
So
S
here
tends to 0,
first S is equal to 0.
this will be 0.
And so you will get limit S tends to 0, 1 by SG.
And why that first S one alone goes to 0?
Because the G, we don't know what the expression is, so we can't cancel that is. S is anyway 0.
If this goes to 0, that will also goes to 0, right? But
No. That the second
unless
S will not go to 0, ma'am.
2 by.
Second S, we don't know. Like, it depends on G.
okay, that makes sense. But since there should be some assumptions that S is negligible unless it is not getting cancelled, right? Okay, I can work on this and let you know about this. I will put a notes in the G
Okay.
chat. Otherwise, I can explain it in the next class. I will work on it and come. I'm missing some term here.
Oh.
Okay, thank you so much.
Okay, thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you.